Autoionization of water. So we mentioned on Monday that water is amphoteric. It can act as either an acid or a base. But what's really cool about water is that it can autoionize. It can act as an acid and a base with itself. So that's what this is describing here. We have one water molecule and another water molecule, and this one's going to act as an acid and donate a proton to the base, and they should have reversed these, but that's okay, because this one came from this guy, and this one turned into that guy. But water can act as an acid and a base with itself. Now, what would be the motivation for that? What would be a driving force for that? Doesn't nature usually try to make things the same as opposed to just having things spontaneously become different? Well, this again is an equilibrium, right? And so it's going both ways. And you probably won't be surprised to find out that the equilibrium constant for this reaction is very small. It only happens to a little tiny extent. The equilibrium constant is 1 times 10 to the minus 14. So that's pretty small. So here's another one, another K. So we had Kc, Kp, Ka, and now we've got Kw. Kw is the ion product constant for water. So that's the equilibrium constant for the self-ionization of water. So water going to H plus and OH minus. So because water is a liquid, Kw ends up being the hydronium ion concentration times the hydroxide ion concentration, or the hydrogen ion times the hydroxide ion concentration. So at 25 degrees Celsius, Kw is 1.0 times 10 to the minus 14. That's a number you should remember. What this means is that in pure water, the hydronium ion concentration is equal to the hydroxide ion concentration. Right? Because if you have one water molecule, you get one of those and one of those. You can't get them lopsided, right? So pure water, equal concentrations. We can calculate that then. If those are equal and you multiply them together to get Kw, then they must equal the square root of Kw, and they end up being 1.0 times 10 to the 7th, minus 7th, sorry. And that should have an M. No, that doesn't work. It's a concentration. 1 times 10 to the minus 7 molar. Those concentrations of ions are very small. Does pure water conduct electricity? No. Have you ever seen one of those conductivity demonstrations? You got the light bulb and the 2 probes and you stick it in water and the light doesn't turn on. If you use tap water, it glows a little bit. Why would that happen? There's ions in tap water. And so if you're outside in a bad thunderstorm, why is it dangerous to be around bodies of water? Well, are those bodies of water pure distilled water? No, they're full of all kinds of stuff, right? And so they do conduct electricity. But pure water is neutral because the concentrations of hydronium and hydroxide are equal. So an acidic solution is going to have extra hydronium ions. You put acid into the solution, you've got an acid that creates additional hydronium ions. But that ion product constant is still true. And so what that means is that if we're adding hydronium ions, the equilibrium must shift to the left towards the water, and that will cause a reduction in the hydroxide ions. And so the product of the hydroxide ion concentration and the hydronium ion concentration is always going to be the same. But the concentrations of the hydronium and hydroxide ions do not have to be the same in a solution where something else is present. And so in an acidic solution, you've got more of the hydronium. And in a basic solution, you've got more of the hydroxide ion. So you can look at the relative concentrations and see if if the solution is acidic or basic. Bless you. So, when I was making these slides, I was thinking, these little calculations here seem pretty trivial compared to the stuff we did in chapters 13 and 14. We're going to do them anyway. So calculate the hydronium ion concentration at 25 degrees Celsius for each solution. Determine if the solution is acidic, basic, or neutral. And they gave us the hydroxide ion concentration. What do we do? Well, we need that Kw expression. Kw is H3O plus times OH minus, and that equals 1.0 times 10 to the minus 14. It doesn't have a unit because it's an equilibrium constant. So then here, the hydronium ion concentration would be equal to Kw divided by the hydroxide ion concentration. You guys follow the rearranging on that? Bless you. So we've got 1.0 times 10 to the minus 14 divided by 1.5 times 10 to the minus 2. And that's going to be 6.7 times 10 to the minus 13 molar. Don't rotate on me. Any questions? Is that acidic or basic? Basic. There can only be one. I miss Juan. I had Juan in my class last semester. It was fun. Well, this is one of those questions, is this acidic or basic or neutral, where it's easy to get the answer backwards, right? So there's different ways to look at it. We can just compare these concentrations. Remember that these are negative, so a larger negative exponent makes the number smaller. This number is smaller than that number. The hydroxide wins, it's basic. So that one's basic. The other way to do it without calculating both of them is to remember that in neutral, pure water, the concentration of each is 10 to the minus 7. And so you can look at this and say, well, is that more or less than 10 to the minus 7? That's higher than 10 to the minus 7. There's more hydroxide, it's a basic solution. So let's answer the acidic, basic, neutral question for this one without doing the calculation. It's neutral. And what is the hydrogen ion concentration? It's the same, right? I mean, we could do the whole setup here, right? But it's going to come out, it's going to be 1.0 times 10 to the minus 7. So that one's neutral. What about the one at the bottom? Acidic, basic, or neutral? That's going to be acidic, because the hydroxide ion concentration is less. That means that the hydronium ion concentration is more. So let's just do this. So that'll be 1 times 10 to the minus 14 divided by 8.2 times 10 to the minus 10. One 1.2 times 10 to the minus 5.
That is bigger.
Yep. That is larger than 10 to the minus 7. The hydronium ion concentration is larger. That's acidic. meant to say acidic. Any questions? pH scale. So the pH scale is just a compact way of specifying the acidity of a solution. If we go back real quick to these numbers we came up with, these are all over the place. 10 to the minus 2, 10 to the minus 13, that's 11 orders of magnitude. Try graphing that, right? You lose all the detail because you've got 11 orders of magnitude. It just doesn't work very well. Oops. So the pH scale compacts that by using base 10 logarithm. So pH is defined as the negative logarithm, base 10, of the hydronium ion concentration. Negative log is not the anti-log, okay? It just means take the log of it and change the sign. It's just -1 times the log, okay? So if we have a solution with a hydronium ion concentration of 5.3 times 10 to the minus 8, what's the pH? Forgot to press the marker button. Well, it will be negative log of 5.3 times 10 to the minus 8. So 5.3 EE minus 8. And that's going to give me 7.27572413. That's not a very good 7. It looks like a 2. It's a 7. So, significant figures and logarithms. So, let's just do something else here. Let's find the pH of a solution that is 5.3 times 10 to the 4th, -4th. That's going to be 3.27572413. Did I get it right? I can do logs in my head. Let's do another one. How about 5.3 times 10 to the minus 12? It's 11.27572413. It's like when James was 1, and I tell people, he knows his colors already. I say, what color is the sky, James? Blue. What color are your pants? Blue. Everybody's all impressed. What color is the grass? Blue. You just have to ask him the right question. What color is anything? The answer was always blue. There's a pattern here, isn't there? The decimal portion of these numbers is all the same. And what's the same about these three numbers? The coefficient part. This is an 8, that's a 7. This is a 4, that's a 3. This is a 12, that's an 11. This is one less than the exponent. Because 5.3 times 10 to the minus 8 is between 10 to the minus 7 and 10 to the minus 8. What's the log of 10 to the minus 8? It's -8, and then you put a negative in front of it, and it becomes 8. So the log of this number should be between the negative log of 10 to the minus 7 and the negative log of 10 to the minus 8, right? Okay, so I'm showing you this to help you understand why the rule for significant figures for pH is what it is. This 7, this 11, this 3, those came from the exponent. Those are placeholders. Those aren't significant figures, are they? No. The 5 and the 3 are significant figures, and they show up in the decimal portion. So if the number you're taking the log of has 2 significant figures, then you keep 2 decimal places. You don't count the digits before the decimal point because they come from this exponent. Once you see that, it's easy to remember. So this would be 7.28, and this one would be 3.28, and that guy down there would be 11.28. We don't want to misrepresent the accuracy of our information when we record the results of calculations. Any questions? So now we got a couple pictures of the pH scale. So here's pH. pH runs from 0 to 14. 14 being more basic, 0 being the more acidic. And here are the hydrogen ion concentrations. And so the negative log of 10 to the minus 7 is 7. The negative log of 10 to the minus 3 is 3, etc. So lower pH is higher hydrogen ion concentration. That can be confusing. You have to just stop and think about it before you record an answer on an exam. Oh, the pH is lower, it's less acidic. No, if the pH is lower, the hydrogen ion concentration is higher, and so it's more acidic. Why did they do that? To get rid of the negatives. Negatives are a pain, right? So got rid of all the negatives that way. So if we're talking in terms of pH, if the pH is less than 7, it's considered acidic. pH equal to 7 is neutral. pH greater than 7 is basic. Now, it is possible to have negative pH values. So what if we had, like the other day, we used 12 molar HCl. It was in a dropper bottle, but that's pretty strong, right? So hydrochloric acid is a strong acid. So then what's the hydrogen ion concentration of that? It all dissociates, right? Yeah. So it's 12 molar. So what's the pH of that? What's the negative log of 12? My calculator got tired and turned itself off. It's minus 1.07918.246. So pH there equals minus 1.08. That's very acidic. So it's possible to have a negative pH, just to let you know.
How accurate is red cabbage juice at testing the water pH?
That's a good question. Red cabbage, and you can try this at home. We did this in 3A last semester. Really fun. Take some red cabbage and boil it in water until you get a nice red solution, and then try mixing that with different household chemicals and things. And the color changes. I'll show you, I think I still have the picture on my phone, of the range of colors that you'll get. Well, the colors are always going to be the same, but distinguishing the differences between the colors is a little bit hard. And usually when you make up a color scale like that, you have orders of magnitude. You'd have pH 5 and pH 6. Well, that's a factor of 10 difference in concentration, right? And so it's not super accurate. But when you're considering the big wide range of pHs that are possible, it's pretty good. But anytime, like if you've got a swimming pool and you're testing the pH, a lot of times it's got a little color strip with different colors on it, and you put some drops in the water and then you compare, right? And for something like that, you don't need to be super, super accurate in the concentration of the pH. Any other questions? Okay. Okay, so calculating pH from the hydronium ion concentration or the hydroxide ion concentration. So we kind of already did some of this, but let's look at this and predict what's this going to be. It's basic because the hydronium ion concentration is less than 10 to the minus 7. It's going to be 8 point something, right? So let's actually do it. pH equals the negative log 9.5 times 10 to the minus 9. Well, I did something wrong. Oh, I accidentally did natural log because this calculator is weird. It's not my fault. It's the calculator's fault. So I'm getting 8.02. 8.02. Because this has two significant figures, and so we're going to have two decimal places. You got 8.98. Well, let me try that again. Negative base 10 log of 9.5 times 10 to the minus 9. I'm still getting 8.02. This is closer to 10 to the minus 8 than it is to 10 to the minus 9. Yeah. So then this is 8. It's closer to 8. As like if we had if we had 8.5, then this number would be higher. What about this one? How do we calculate the pH? No. Nice guess. Natural log. No. We have to figure out what the hydronium ion concentration is first. So the H3O plus is going to equal Kw over the hydroxide ion concentration. 1.0 times 10 to the minus 14 divided by 7.1. That's not a 1. Times 10 to the minus 3. 1 EE minus 14 divided by 7.1 EE minus 3. So 1.4084507 times 10 to the minus 12. Now, how many sig figs does that number have? It should have 2. Do I want to round that off and then calculate the pH? No, that's not a good idea. You want to keep at least a couple extras. Do you have to type the whole thing in? One of the things I'm evaluating this calculator to see if I like it or not. And one of the things I don't like about it is I can't just take this number and take the log of it. It's kind of annoying that way. Well, it could be that I just am not really knowing how to do the calculator yet. But for now, that's where I am. Yeah, but that's a pain. The other one, I just press a button and it's done. There, I successfully used the answer button. So I'm getting a pH of 11.85. So the pH is the negative log of that mess. And probably, usually 2 or 3 extra sig figs are plenty to avoid a rounding error. And then I report this with 2 decimal places based on the original 2 significant figures. Any questions?
Oh, yeah.
Yes?
For an exam, are we going to be given the KW, or we're going to have to memorize it?
You need to memorize the KW.
For
You're going to, for water, 10 to the negative 14. You're going to use it so much you'll remember it. And that's true at 25 degrees Celsius. I would not expect you to know what it is at other temperatures. So if we did it at another temperature, I'd give that to you. Is there a way to calculate it? I don't know off the top of my head. I'm sure there's tables where you can look it up. I don't know if there's an equation that describes it that would allow you to calculate it, or if it's more like the vapor pressure of water at different temperatures where you just look it up in a table.
So then if 10 to the negative 14 is a KW for water, then 10 to the negative 7 is water also, right?
That's the concentration of the hydroxide ions and the hydronium ions in the pure water. Yeah. Okay, so what about calculating the hydronium ion concentration from the pH? So we use the same formula, but we have to rearrange it. So pH equals negative log of the hydronium ion concentration. But we want to know the hydronium ion concentration. So we need to rearrange this. So the first thing I'm going to do is I'm going to move, here I'll do this in a different color. I'm going to move that negative side. I'm going to multiply both sides by -1. So now I've got negative pH is equal to the base 10 log of the hydronium ion concentration. How do I get the opposite of log? Anti-log, 10 to the x, right? In 3A, students try to divide by log. It just doesn't work. You can't divide by a function. It just doesn't work out that way. It just, not how they're trying to do it, you can't. So we're going to take 10 to the of both sides. So this is 10 to the log of H3O plus, which is equal to H3O plus. Okay, so what we come up with is that the hydronium ion concentration equals 10 raised to the power negative pH. It's helpful to remember that one. So then for this particular example, H3O plus is going to be 10 to the minus 8.37. And that is not the proper format for a number, so don't just leave it that way, please. So get your 10 to the x and put in minus 8.37. Stupid calculator. Sorry, having calculator issues. Minus 8.37. No, that's not right. Good grief. I hate you, calculator. I hate you. Okay.
Is it just unfamiliarity? Or?
It's unfamiliarity. Okay. I'm used to other things, and I'm trying something new, this is why I don't try new things. There we go. Okay, here's a question. How many significant figures should this answer have? 2. Because we have 2 decimal places in our pH. So this is going to be 4.3 times 10 to the minus 9. Any questions? So you should memorize the pH equation. And whether you memorize the other equations related to pH or just figure them out on the fly is up to you. I like to figure stuff out as I go along. It makes life a little more interesting. Yeah, it's just fun. A little risk there without, driving your car off a cliff or anything physically dangerous, right? Okay, so the POH, is it okay? Yeah, it's a sturdy one. Calculator on the floor. POH and other P scales. P is a function. It's a mathematical operator that means negative log of. Okay, so we can have P things other than hydrogen ion. pH is the hydrogen ion concentration. POH is just the negative log of the hydroxide ion concentration. So we'll sometimes talk about the POH. So the POH scale is opposite of the pH scale. They meet in the middle, neutral, they're both 7. But at an acidic situation, the pH is low, the POH is high, and vice versa. So they're just opposites of each other. Derive a relationship between pH and POH. Well, what's the relationship between the concentrations of H and OH? If we multiply them, they equal 10 to the minus 14. So I'm just going to go with hydrogen. I'm sick of writing 3O. H plus times OH minus equals 1.0 times 10 to the minus 14. That's the equilibrium expression for the ionization of water, the self-ionization of water. Well, we've got an exponent here, and we're looking for pH and POH, right? So pH is the negative log of. So let's take the negative log of both sides. So the negative log of H plus times OH minus, and the negative log of 1 times 10 to the minus 14. When you take the log of numbers that are multiplied, you can separate them by adding. So the log of H plus times OH minus is the log of H plus the log of OH minus. Remember from math class, but this is negative. So this is the same as the negative log of the hydrogen ion concentration plus the negative log of the hydroxide ion concentration. And what's the negative log of 10 to the minus 14?
14.
It's 14. Technically 0.00, as we wrote it there. This says 2 sig figs, and so we need 200. This is pH. This is POH. pH plus POH equals 14. That's the relationship. Any questions? Just a little derivation. See, the awesome thing about having a decent understanding of algebra is if you have to, you can come up with stuff like this, right? In some of the classes I teach, they just really don't have a good grasp of algebra, and they can't do something like this. And so then they get into all kinds of trouble with stuff. The circle of life. No, the circle of pH. Okay, so this is the interrelatedness of all of these things. So let's put pH at the top. And this comes out a little different every time I draw it. But pH is related to the hydrogen ion concentration. The hydrogen ion concentration is related to the hydroxide ion concentration. The hydroxide ion concentration is related to POH, and POH is related to pH. That is the circle of pH. So how are these related? Well, let's change colors. How are pH and POH related? You add them together, you get 14. So pH plus POH equals 14. What's the relationship between pH and hydrogen ion concentration? pH equals negative log of the hydrogen ion concentration. What if we wanted to go the other way? The hydrogen ion concentration equals what? 10 to the negative pH. What about hydrogen ion and hydroxide ion concentration? You add them together, you get water. That's true. And you multiply them together, and you get the ion product constant of water. Right? That's where we started tonight. And then what about this, POH and OH?
POH is the negative log.
It's these same equations, but with OH instead. So POH is the negative log of the hydroxide ion concentration, and the hydroxide ion concentration equals 10 to the minus POH. So if you start with one of these, you can get to all of the others. Sometimes there's an easier way and a harder way. We did a problem earlier where they gave us the hydroxide ion concentration and asked us to find the pH. You have a choice there. We went this way. We went to hydrogen ion concentration and then to pH. But you could go the other way as well. You'll get to the same answer. So I think it's helpful to have that idea in your head that these are all related to each other. Ta-da!